Hello! In this video, we are going to prove the following theorem. The harmonic series diverges. Okay, now to show that a series diverges, what we can do is we can show that the sequence of partial sums diverges. Right, so this is the sequence of partial sums for this series, right? And as you can imagine, the terms go like this. 1, 1 plus 1/2, 1 plus 1/2 plus 1/3, 1 plus 1/2 plus 1/3 plus 1/4, and so on. And we're going to show that this sequence diverges. And to do that, the approach we're going to take is we're going to show that this sequence is not a Cauchy sequence. Because if you recall, a sequence is a Cauchy sequence if and only if it converges. Therefore, if we can show that this sequence is not a Cauchy sequence, then it must diverge. And that's the idea. But what is a Cauchy sequence, if you recall? To say that a sequence, say xn, is a Cauchy sequence, means for every epsilon greater than 0, there exists a positive integer k, such that for all positive integers s and t greater than or equal to k, we have that the absolute value of xs minus xt is less than epsilon. Right, so that's what it means. But really, we want to show that our sequence is not a Cauchy sequence. So, what does it mean for a sequence to not be a Cauchy sequence? Well, it means exactly the negation of this statement. So, we're going to negate this statement to figure out what that is. So, for a sequence to not be a Cauchy sequence means it is not the case that for every epsilon greater than 0 that this is true. In other words, there is an epsilon greater than 0 such that this is false. So there is an epsilon greater than 0 such that this is false. Well, what does it mean for this to be false? It means that there does not exist a positive integer k such that this is true. In other words, for every positive integer k, this is false. So for every positive integer k, this is false. What does it mean for this statement to be false? It means it is not the case that for every two positive integers s and t greater than or equal to k, that this is true. In other words, there are two positive integers s and t greater than or equal to k such that this is false. What does it mean for this to be false? It means the absolute value of xs minus xt is greater than or equal to epsilon. Right, so that's what it means for this sequence to not be a Cauchy sequence. And so we're going to prove that this statement is true for the sequence of partial sums. So let me rewrite this statement up here, where I'm going to replace xn with hk, and we're going to replace xs with hs and xt with ht. So, we're going to show that our sequence of partial sums is not a Cauchy sequence by proving this statement. Now, to prove this statement, we need to find a positive integer that satisfies this statement. But our claim is that 1/2 will do it, right? 1/2 will satisfy the statement, and we're going to prove that. So really, with 1/2, we're going to prove that this statement is true. And we're trying to prove a statement about every positive integer. So give me an arbitrary positive integer. I'll call it k. And with this arbitrary positive integer k, we want to prove that this is true, right? We want to find two positive integers, s and t greater than or equal to k, that satisfy this condition. Well, guess what? Our claim is that 2k and k will satisfy this condition. And what we would like to show now is that the absolute value of h2k minus hk is greater than or equal to 1/2. Now check this out. h2k is really the sum from n equals 1 to 2k of 1 over n. And hk is the sum from n equals 1 to k of 1 over n. Now, it turns out that this sum is greater than this sum. The reason why is because the sequence of partial sums is a monotone increasing sequence, right? Each term is bigger than the one that came before it, right? And that makes sense, and I think you guys can agree with me on that. So, because this is bigger than this, it follows that this expression is positive, and so we can just remove the absolute values. But now, we would like to show that this is greater than or equal to 1/2. Now, we can conclude that this is true if, for every positive integer w, the sum from n equals 1 to 2w of 1 over n minus the sum from n equals 1 to w 1 over n is greater than or equal to 1/2. If this is true for every positive integer, well then, since k is a positive integer, it will follow that this is true. So we will indeed have that the absolute value of hs minus ht is greater than or equal to 1/2, as we want it to be. So now it suffices to show that this is true. And so we're going to prove this by using mathematical induction. So to start, let's prove the base case, right? Let's prove that this is true in the case where w is equal to 1. So really, we're going to take the sum from n equals 1 to 2 of 1 over n minus the sum from n equals 1 to 1 of 1 over n. Now, of course, this first sum is really just 1 plus 1/2. And this second sum is really just 1. So we're subtracting 1. And this is equal to 1/2. So yeah, this is greater than or equal to 1/2, as we wanted it to be. Right? So we have proven that this is true in the case where w is equal to 1. So this concludes the base case. Now let's move on to the induction step. And I'm going to have to move back to the top, so just so we don't lose any information, let me rewrite that the sequence hk is defined by this formula. Now, I put a ... here just to indicate that there's more details that came before this. So now let's move on to the induction step. In the induction step, we're giving ourselves an arbitrary positive integer where this is true. And now, we want to prove that the same thing is true for w plus 1. And so to do that, let me write out this thing where instead of w, we have w plus 1. Okay, now, in the top of this first sum, I'm just going to rewrite this as 2w plus 2. Okay, now in this first sum, what we're going to do is we're going to rewrite this as the sum from n equals 1 to 2w of 1 over n plus 1 over 2w plus 1 plus 1 over 2w plus 2. Right, so really we just pulled away the last two terms of this sum and rewrote the sum as this. And similarly, we're going to pull away the last term of this sum so that we have the sum from n equals 1 to w of 1 over n plus 1 over w plus 1. Right, so just like that. And next, I'm just going to regroup some of the terms here. Notice we have this minus this. And then we have plus this, minus this. Now, by the induction hypothesis, we know that this is greater than or equal to 1/2. So since this is greater than or equal to 1/2, it follows that this entire thing is greater than or equal to 1/2 plus this minus this. Next, notice that 2w plus 2 can be rewritten as 2 times w plus 1. And I can take this fraction and multiply 2 in both the numerator and denominator. We see that if we combine these two fractions together, we get minus 1/2 times w plus 1. Right, so we can all agree that these two are equivalent, but really, we know that this is just 2w plus 2. And since 2w plus 1 is less than 2w plus 2, it follows that 1/2w plus 1 is greater than 1/2w plus 2. Therefore, this part is positive. So we have 1/2 plus a positive number, which means that this entire thing is greater than 1/2. And so that proves that this is true, where instead we have w plus 1. And that's it. This closes the induction. So at this point, we have proven that this is true. And that allows us to say that the absolute value of h2k minus hk is greater than or equal to 1/2, as we had done before. So yeah, we have proven that this is true. So that proves this statement. As a result, we have proven that the sequence of partial sums is not a Cauchy sequence. But remember, if you're not a Cauchy sequence, then you're not convergent. In other words, you're divergent. So the sequence of partial sums diverges. Therefore, the harmonic series diverges. And so this completes the proof. And so yeah, that's pretty much it for this video.